Okay, so we are live now. So, welcome everyone to TCS Plus. Today's speaker is Thatchaphol Saranurak from TTI Chicago. Before we start the talk, let me just uh, thank my fellow organizers, Clement Canon, Ajay Raghav, Thomas Vadik, Ilya Rosenstein, and Gautam Kamat. And we'll now go around the table as is usual and introduce all the groups. So first we have the group from Caltech. Hello, Caltech. Then we have the group from France. Hello. Then we have the group from Indiana. Hello. Uh, then we have the group from BRC in Copenhagen. Hello. And then finally we have the group from Michigan. Hello. So we are still waiting for a couple. Another group might join us in the meantime, but okay, let me stop the presentation. Okay, and so today's speaker is Thatchaphol Saranurak, who is now a research assistant professor at TTI Chicago, and previously did his PhD from KTH, and he has worked on a number of problems in data structures, dynamic algorithms, graph algorithms, and today he's going to tell us about very recent result on vertex connectivity. And before we start with the talk, just one more reminder: during the talk, you will be muted, but unmute if you want to ask a question, which is encouraged. Just unmute yourself. And 2 weeks from now, we have Chris Pikert. So anyway, okay. So the floor is yours.
Thank you very much, Anindya. And I must say that thank you a lot for organizing this. I'm a fan of this TCS Plus for a long time, and it is an honor to be here. Okay, so let me start. So this is a joint work with Danupon Nanongkai, my PhD advisor when I was a student, and Sorachai Yingcharan Thawonchai. He is a PhD student and he is moving to Aalto University in Finland soon. By the way, you can hear me well, right? Okay, good. So this talk is about vertex connectivity. So to start, let me tell you the first definition, which is K-connectivity. So we said that the graph is K-connected if we cannot disconnect a graph by removing less than K nodes. So basically, if you look at any set of vertices S, which is of size less than K, then it must be the case that once you remove S, then G still have one connected component. For example, if you look at this graph, G is 2 connected because if you remove any one node from it, it is still connected, but G is not 3 connected because of this set S. Okay. So the question that we ask is just really a basic question. In classical setting, we are given a graph with n nodes and m edges, and we ask if G is K connected. And there is a long history about this problem. When K is 1, this is really just asking if the graph is connected. We can do breadth first search or depth first search in linear time. When K is more than 1, K is 2 or 3, Tarjan and Hopcroft have found a linear time algorithm as well. But then because of this, it is asked in the book by Aho, Hopcroft and Ullman since 74 that maybe there is an algorithm, linear time algorithm to check K connectivity for any K. But it turns out that even for K is 4, it is not clear how to do this. And in linear time and in the Fox paper by Kenevsky and Ramachandran, 91, they managed to get Nsquare time, but it is still not near linear in number of edges. So it gets stuck like this for a long time. But as a side note, for a very closely related problem, K-edge connectivity, where you ask the same question, but you ask how many, like, can the graph be disconnected by removing less than K edges, less than K edges. So it turns out that this problem is almost settled, like 20 years ago, more than 20 years ago, like by Karger. We know how to solve this in near linear time for any K. But for vertex connectivity, this is still the state of the art. Okay, but we can ask, what do we know about the problem when K is large? For general K, we can ask another question. So this can be solved trivially just by running MaxFlow Nsquare time. Basically, we check for each of the pair of the vertices, whether like you check if the MaxFlow from S to T for every pair ST have size at least K, and this can be done in MK time. It's known how to do it by Ford-Fulkerson, right? So this is a trivial way to check K connectivity, and then people have tried to improve this, and basically the work by Becker from 82 can do this not from every pair, but from only n pair. Essentially, this is like computing. The algorithm itself is essentially computing a single source MaxFlow. So instead of every pair, you check you compute ST MaxFlow from some node S to every node T. This is essentially the algorithm. And then there is other cool algorithm by Linial, Lovász, and Wigderson that basically give a physical interpretation of vertex connectivity. Like, oh, 1 second. And basically, it is about checking degeneracy in rubber band networks that I won't go into, but it have some cool idea in it. And then a work by Nagamochi Irabaki says how to say that we can assume that the graph is quite sparse. M is like NK. And then people like Henzinger, Rao, and Gabow show how to solve this problem in MN time. And the idea in this work is really to show how to solve single source MaxFlow, like the work in Becker et al. In MN time. And this is actually very cool because it says how to solve MaxFlow in OM time amortized, right? So this is actually a cool thing to know. And there are like there are some slower algorithm, but deterministic, and it's used some cool idea like Ramanuja expanders by Gabow. Okay. So this seems like a complicated history, but once you see that if you look at the special case when the graph is sparse, when M is N, hence K must be constant, this becomes much more simplified. But you see, despite of many ideas from a long time ago, the Nsquare bound remains here since 69. So just recently, in our work in stock, we break this Nsquare bound from to n to the 4/3. And actually today, I will tell you how to solve this in linear time, near linear time. So actually the bound that we have is something like this. It's n k squared times m. with polylog factor. So basically, looking back to the case when k is small, we basically get the near linear time algorithm for any constant k. So what we have, the result is that it proved the conjecture by Hopcroft and Ullman from 74, when k is constant up to polylog factor. It breaks this 50-year-old bound of Nsquare down to linear. And it is the fastest algorithm when k is not too large. So this is a result. And actually, we have some other result that is actually the algorithm can be extended to two-directed graph with the same time, mk square. And just to compare a bit with the related question, kh connectivity in directed graph, here we don't have near linear time yet. The best known is mk. So the algorithm here is quite the running time here is quite close to edge connectivity. And we can actually do 1 plus epsilon approximation in a faster time. It will be mk over epsilon. So this is a result. And the conceptual message, the take-home message about this work that I want to make is this. If I have a time machine, I could tell the people in the 90s that what really is the core of this work is to try to solve the problem locally. We will see what we mean by that in the end, at the end of the talk. And the same thing can be said to the people in the 70s, but then people didn't use randomization that much, so we need to say that try to solve it locally and use randomization. That is, like our algorithm, you will see that it could have been found a long time ago. It used a basic technique from a long time ago. Okay. So any question about the result up to this point? Okay, let me continue with some definition. So the basic definition is vertex cut, L, S, R, L for the left, S for separator, and R for the right. So LSR is a vertex cut if L, S, and R partition this set of vertices, and L and R are non-empty. And more importantly, there shouldn't be any edge between L and R. So the neighbor of L is S, and also the neighbor of R is S. Okay, and the size of this cut is just the number of nodes in S. This is another example of vertex cut. So next thing is the ST connectivity, which I will denote it by kappa of S and T. This is just the size of mean cut when S is on the left and T is on the right. And just to recall again, we can check easily, straightforwardly, if ST connectivity is at least K by running Ford Fulkerson in MK time. And just to make sure that we are on the same page, K is K connected if the kappa ST connectivity for every pair is at least K. So now let's begin with the overall algorithm, our framework. So the goal is this. Suppose that you have a graph, and suppose that your graph is not K connected. Okay? That is, there exists a cut SLR such that S have size less than k. So, and let me assume that the volume of L is less than the volume of R, and the volume is basically is just defined as the sum of the degree in the set. Okay. So the goal here is to do this. We want to do that with high probability. We want to find some cut L prime, S prime, I prime, such that the S prime is less than K. And if G is K connected, then we just declare that the graph is K connected. If it's not, we want to find some cut S prime. Okay. And there are two cases. First, let's see the easy case. That is, the cut here, L and R, are quite balanced in the sense that the volume of L is quite large, M over K, at least M over K. So here, just a simple observation. Suppose that you sample K pair of edges, E and F, okay, something like this. You sample E and F here. Then with high probability, there should exist one pair, such that an endpoint X is on the left and another endpoint Y is on the right. This is really because the size of the volume of L is at least M over K, right? And R is like at least M over 2 or something like that. So if you do this K sampling, K log n sampling, then with high probability, one of the pair will be on the different side of a cut. But once you have this, it suggests a very simple algorithm. So what do we do? We just do this. For each sample pair EF, you just check if the connectivity from X to Y is less than K. And if it is the case, then the Maxflow algorithm will return you a cut. And we know that so we know that the pair like that the pair that are on the different side must exist with high probability. So we will get a cut with high probability. So in this case, the running time is just simple. It's just K times MK. So this is MK square time to detect some cut if L and R is quite balanced. Okay. So in the next case is when the cut is not balanced. So L is so small. Thing like L is so small here. Okay. So suppose that the volume of L is something like 2 to the I. So the idea is kind of the same. If we sample M over 2 to the I edges times log factor, something like that, and one with high probability, one of the sample edge, you will have that the endpoint is inside L. The endpoint X is inside L. Okay. So once you have that X is in L, what do we want to do next? Right? What we want is we want to find a separator S here that is near X in time. If we can do it in time 2 to the I, like sublinear. If we can do it, then the time will be the total time to do this will be linear, right? But note that the time that we have, we cannot spend even linear time per sample. We want to spend sublinear time to detect if we are given X and we want to find a separator S in sublinear time. This is what we want. And this is really the new key tool that we will talk about soon. But informally, what is this tool? It is called local vertex connectivity. And informally, it does the following. So given a seed node X, then it will find a set L that contains X that has small volume, and it has a cut size less than K in sublinear time. Basically, this is exactly what we want. So to make it more formal, it is a procedure local X new K, and K is and X is a node. And we need also that new is at most K, MOK. And it does the following. It either declares that there is no set L containing X such that the cut size is less than K, like the number of neighbor is less than K, and the volume is smaller than new. Or it finds you a set L such that the cut size, the number of neighbor is less than K. Okay. And what we can do is we can do this in new K square time. So if K is constant, this is really just proportional to the volume new here, and there's no dependency on N. So given these two, then it perfectly fit into the framework, right? So we sample M over 2 to the I edges. One of the endpoint X will be in L. Then for each of the sample, if we just run this local algorithm with the parameter X 2 to the I and K, then with high probability, it will find you a cut, right? Because with high probability, one of the endpoint X is in L, and the local algorithm cannot declare that there is no cut because there is the cut. So it will find you a cut. So to conclude, in this case, you have that the running time is M over 2 to the I times 2 to the I times K square. So this is MK square again. So this is really the algorithm. There are two cases when to handle the case when the cut is quite balanced. Here we sample K pairs of edges and we check the connectivity between X and Y, the endpoint of the two edges. So this will detect a cut if the cut is balanced. And other case when the cut is not balanced, we just do this for each 2 to the I. We detect it in time MK square as well. If you cannot detect any cut in both cases, you just declare that the graph is K connected.
Can you go back to the slide on the local algorithm?
Yeah.
So on the local algorithm, where exactly do you require like this non-balancedness condition? Like, I mean, what if you just put I equals log M over K? Like, and why do you have this two? I didn't understand why do you have this dichotomy kind of.
Yeah. So the algorithm really work when new is less than M over K.
Oh, okay. Sorry.
Yeah. Mm-hmm. So you will see why. It will be clear from the algorithm. Yeah. But yeah, if you don't have this constraint new less than M over K, you can just use local algorithm for the whole range. Okay. Okay. So if the framework clear, so now what is left is really just how to do this local vertex connectivity, right? If we can do it in new K square time, then we are done. So this is what we are going to do next. So, okay, just to remind you again, we have two cases, right? Given x, nu, and k, we either declare that there is no local cut in the sense that the volume of L is smaller than nu, and the cut size is less than k. We declare that there is no such cut, or we just find some cut of size less than k. So this is a goal. And it turns out that what we will talk today is this algorithm, new k-square. This is the simplest one, and it is actually inspired by the work by Cecik, Hansen, Italiano, Loisenbauer, Parositis in Soda 17, where they managed to get an algorithm with new k to the k, and they actually use in the different context, which is the maximal kh connected subgraph, and what we have before is in our stock paper have running time new to the 1.5k. This is based on a more general principle, like it is more complicated, but based on a more general approach, like called local flow. So the story is really like we show how to do it we show how to get the result in our stock paper first, and then we try to see more application of our work in stock, and it turns out that the work by Cecik et al. Can get better dependency on new, and inspired by this, we get new k-square. But you see that this new k-square algorithm is so simple.
Sorry, I've got a small question about the deterministic versus randomized. So, I mean, I understand that it's better to get deterministic, but even if you were to get a deterministic version, the whole algorithm would still be randomized because of the first case, right?
Exactly. Yeah. So the framework itself is randomized. So even if you have local deterministic algorithm, everything is still randomized. Yes. Mm-hmm. So this is the history of this local algorithm, but I would like to mention a related problem called local approximate sparse cut, which many people might be more familiar with. So this is an algorithm for finding approximate sparse cut, like something like nipple or page rank algorithm, which have been devised by Spielman and Teng and Anderson, Chung, Lang, and also like a flow-based one by Orochia Zhu and Henzinger, Rao, and Wang. But I would like to stress that this is an approximate problem, and our problem is exact. It is about checking whether there is a cut of size k or not. Okay. So let's see how to solve this local vertex connectivity. So the first thing is to just reduce it to directed edge connectivity, because it's easier to think about. So here again, we have local vertex connectivity problem. What we want to reduce to is local edge, directed edge connectivity. It is almost the same problem. The difference here is really that here we would like to check if there is a cut such that the number of edges going out from L is less than k, instead of the number of neighbor of L. We just check the number of edges going out from L is less than k or not. Okay. And the volume here, again, is just to remind you, this is the directed graph, and I define the volume to be just the sum of out degree and in degree. Okay, so this is almost the same problem, and it is using the standard reduction. We will see how to reduce from vertex connectivity to directed edge connectivity. So the standard reduction that we see in when we solve MaxFlow in vertex. This is the same the reduction for reducing from vertex MaxFlow to directed edge MaxFlow, right? So given any edge UV, you just for each of the vertex you split it into U in and U out, and for V you split it into V in and V out, and then you draw the directed edge between U in U out, V in from V in to V out, and if there is an edge from U to V, you draw an edge from U out to V in and V in to V out, V in to U, V out to U in, sorry. Yeah, so this is a picture, and for like a seed vertex X, just to simplify things a bit, this is nothing much. I won't split the node X, okay? So this is standard reduction, and suppose, just to convince you by picture, if you look at any cut L, any set L containing X here, with the number of neighbor, with this NL neighbor, once you do the reduction, you'll see that the number of neighbor L and the number of edge that going out from L prime, they are the same. The number are the same, and the volume are like within the same constant, within some constant factor. So this reduction, it preserves the size of the cut exactly, and the volume is almost the same. Okay, so just by this reduction, it is quite clear that we can just work with this problem, directed edge connectivity. So this is what we will focus on from now. Okay, so let's try to see how to solve this local directed edge connectivity. Okay, so let's, as a warm-up, let's see the simplest case. That is, suppose that there is a set L here, and there is only one edge that going out from L, and moreover, there is no edge going into L. Okay. How do we check? How to detect such L in this case? When the situation is this simple, it is quite straightforward to detect L. How? So suppose that you just do some search, like depth first search or breadth first search from X, and suppose that you explore exactly new plus one edges. Okay, so more than new edges. So if you do this, we know that your search must go out of L. Why? Because the volume of L is at less than new, right? So you must go out at some point because you explore more than new edges. But once you do this, you know that you stop outside L. Now suppose that you reverse the path from X to the endpoint that you stop. Then you know that now once you reverse the path, the cut size of L will become 0. It will decrease from 1 to 0. And now you know that if you do the next depth first search again, you will get stuck at L because you cannot go out from L. Okay, so this is a simple observation. in this simple case. But what if there is some edge that can go into L, right? By the way, I would like to mention also that this observation is also like observed already in the work by Chechik et al. Okay. And now, what if there is some edge going into L? Then it is not as simple as before. Why? Because the depth first search might end inside L. Even if you explore like much more than new edges, you might go out of L, but then you might like eventually come into L. So if this happens, even if you do the path reversion, it won't reduce the size of a cut. The delta out of L will not be reduced, and we cannot make progress. So what's the idea? The idea is, this is a key idea and very simple one. We just do the sampling on some explore edge, where the explore edges is just the edge that you have read. So suppose you sample an edge, right? You sample an explore edge y prime to y, but because we know that we have explore much more than new edges, so most of the explore edges are outside L. So if you sample this edge y prime to y, so y should be outside L. This is it. And if you know that y is outside L, then again, now if you reverse the path from x to y, it will reduce the size of the cut, and you make a progress. Okay, so this is the idea. So now let's see how to make this idea the whole, how to go from this idea to the whole algorithm. The algorithm works like this. So you repeat for k times. For each time, you grow DFS3T starting from x and explore exactly k times new edges. So you explore from x and for k times new edges. It might go inside L again, but by the way, if you get stuck somehow, you will find some cut L prime and you just terminate it. Okay. And you will return this cut L prime. But if you don't get stuck, you just sample and explore edge y and y prime. Okay. Sample it. And then reverse the path in this from x to y. And you repeat this k times. Okay. If you get stuck at some point among this repetition, you return a cut. If you don't find any cut, you terminate with a no cut. Okay. So this is a whole algorithm. And what we need to show is 3 things. First, we need to show that the running time is new k square. Second, we need to show soundness. That is, if L prime is returned, then we must show that originally in the graph, the cut size, the number of edges that go from L prime to the outside is less than k. And for the completeness, we need to show that if there is no cut return, then with some probability constant, then there is no cut that is of small volume and small cut size less than k. And by the way, this probability 1/10 is no problem, because if you have it, you can just repeat log n time to get with high probability guarantee. So three things we have to show. And the first thing is very simple. We repeat k times, and each time the whole algorithm is really just do DFS to explore k times new edges. And to explore k times new edges, this is really like the time to do DFS is proportional to the time you visit each edges, right? So this is the time. The time here is really just k times new time, k times new k. So this is new k square. So this is done. How about soundness? That is the cut. If we return, it should have small cut size. So just one observation first. If L prime is returned, right? So observe that there were less than k path reversions before we return L prime. Why? Because I mean, we might have repeat this k minus 1 times, right? And in the last iteration, if we don't stop before that, in the last iteration, we return a cut L prime before we reverse the path in the kth iteration, right? So if we return L prime at all, there were less than k path reversions. Okay. So now, so now let's see. If we fix any L prime set, any set L prime that contain X, okay, and suppose that we reverse the path X to Y, then there are two cases. Suppose that Y is not in L prime, the first case. Then you see that the number of times that this path going out from L prime must be more than the time that it go into L prime, exactly 1. So if you reverse the path, then the cut size is decreased by exactly 1. Right? On the other hand, if Y is inside L prime, then the cut size will stay the same. So just by this observation, right, we know that if we return the cut L prime, we know that we must get stuck at L prime, which means that at the end, the cut size of L prime have become 0. But there were less than k path reversions in the algorithm. So so we know that the cut size must be less than k initially. Is this clear? Okay.
Sorry if that was clear, but what is exactly the L prime you return?
Right. So the L prime that we return is just a cut that you get stuck. Like you run your algorithm, right, and you reverse the path for each of the iteration. Then the graph change a bit, and if you run your DFS tree and you cannot explore, you get stuck before you can explore k new edges. Like here, you get stuck at L prime like this. Before you can explore k new edges, then you just return what you have, all the node that you have explored. This is L prime. So L prime is all the node that you have explored when you get stuck.
Thanks. And I have another question. So I guess since the previous work was deterministic, the main difference is in the sampling. How exactly did the previous work get k to the k? What was exactly the difference in what they were doing?
So the difference is that they need to branch, like they do some kind of branching, like for each of the iteration, k iteration, they do k branching, and they search. They for each of the branching, they search. They spend like new k time, something like that. But because of this branching, okay, there is k iteration, and for each of the iteration you do k branching. So this is how k to the k come from. Yeah, but here we don't do branching because just by randomization you get something outside. So and the reason they do branching is really because they want the endpoint that is outside L. Yeah. Okay. So the sound is it's clear, right? So now should I proceed to the completeness? Okay. For the completeness, we just have to show, right, that if no cut is returned, then there is really no cut L containing S that have small volume and small size. So just suppose that there exists such L, right, where the volume is small and the cut size is less than K. So here we see that once you sample and explore edge y prime and y, we know that y shouldn't be in L with probability at least 1 minus nu over k nu. Why? Because the volume of L is less than nu, but we have explored k new edges. So sample one of these edges should be outside L with this probability, and this is just this simplified to 1 minus 1 over k. And once you do this, once if you have that y is outside L, then when you reverse the path, the cut size must be decreased by 1. And then if you after k minus 1 iteration, the probability that y is outside L in every iteration is quite high. That is, suppose that y is outside L in every iteration, then you know that then the cut size of L will be decreased to 0. And this happens with probability at least 1 minus 1 over k to the k minus 1. And this is less more than 1 to the 10, 1 over 10. Right. So once you know that after k minus 1 iteration, the cut size becomes 0, then in the last iteration, you must get stuck, right? You must get stuck, and you will return L prime, and L prime might be L. Yeah. So basically, if this L exists with L with small volume and small cut size, then we will return a cut with probability at least 1 over 10. So this complete the proof. So just to recap, right? And in the we know from this we can solve the problem for local directed edge connectivity in time new k square, and just by a standard reduction we get local vertex connectivity. Okay, and from this we plug into our randomized framework, and we get an algorithm that run in mk square time. So this is the algorithm.
Sorry, I've got yet another question. To go back to what Aninia has asked, what exactly is the part in the second?
Good. Yeah. So you see that here we explore k times new edges, right? And we need to assume that new times k is less than the whole graph. Yeah. Otherwise, we always get stuck. Yeah. So this is why new must be less than m over k. Okay. So this is the algorithm. So to conclude, we just showed the algorithm that run in k square m times. It is randomized, and you can see that it is quite simple. I think it is teachable. Maybe it is implementable, and it does. Although it is quite simple, it proved the conjecture a long time ago, and it breaks this Nsquare bound from 50 years ago. And it is fastest when k is not too large. And the key tool is really this local vertex connectivity. And I think maybe one can do it in new k time, but I don't know how to do it yet. And as you see, the algorithm really used the technique from 70s. And we just, the key message that I would like to convey here is really maybe trying to solve something locally is the key to get faster algorithm for many problems. So next is the Orion question. So as you see that this algorithm is really randomized. Can you do it deterministically in near-linear time as well? So recently we actually can break N² time down to not linear yet, but n to the 1.8 using some completely different technique. But local algorithm is needed actually, but we need many more other ingredients. But I think it is very challenging how to do it in linear time deterministically. And our algorithm is for small k. What if k is large? The best known algorithm, all algorithm that is known still have n cube time when k is large. Can we break this bound? Or even in weighted graph, we don't know how to break mn time. For another end, another extreme, suppose that we insist on near linear time algorithm, no dependency on k, right? Can we get some maybe approximation algorithm? Right now, the best known near linear time algorithm have log n approximation. This is by Sensor Hillen, Ghaffari and Kuhn. Can you get better approximation? And the next thing is single source vertex connectivity. So this problem is similar to is the problem where you fix some source S and you want to check whether whether for each vertex T, whether the connectivity from S to T is at least K. Okay. So we don't know how to break N² time. And I would like to say that this is really like the barrier for all other previous results. The reason why our previous result cannot break N² time is because they actually try, their technique actually can solve single source vertex connectivity. And maybe one can break this bound, or maybe there is a conditional lower bound, but both upper bound and upper bound we don't know. So I think it is interesting. And for this local algorithm, can you get it faster? And maybe I expect much more application for this kind of thing. Yeah. So this is it. Thank you.
Thank you. So do we have any questions? There is some time left. We can have a few questions. So we had some during the talk as well.
Yeah, I have one question again. Has there been any work on the promise problem? Like if I promise you that the graph is far from K connected, can you find something or?
Okay. Sorry. So I don't know on top of my head. So this is like maybe property testing kind of stuff. I expect that there should be like devising local algorithm, like sublinear time algorithm for this kind of setting should be more approachable. But I don't know on top of my head. Yeah.
So I have a question in that context. So if the K vertices are like really, suppose the graph could be split with some K vertices, okay, but the K vertices are like really hidden in one corner, and let's say K is 2. Without seeing every edge or vertex, how are you going to potentially even know the existence of such vertices?
So
right?
Yeah, so this is really why, like, when to detect this thing, you really like sample. You really start from every node or from every edge.
Right.
Yeah.
Yeah. So I'm like, this doesn't seem like something where, like, even if there's a gap of K versus 2K or something like that, unless there's a huge gap, like K versus N over K, not entirely sure why there's sublinear time algorithm. Like,
yeah.
Lamász approaching maybe has something to say.
Yeah, no, it's the promise would not be that it's K versus 2K. It would be like you need to change at least an epsilon n fraction of the matrix to make it.
Okay.
Right. Yeah.
And when you said the open question about the weighted version, you meant like not directed, just the graph, and you now put weights on every vertex, and you want to know if there's a small weight vertex separator.
Yeah.
Is that the thing?
Yeah. Okay. Exactly. So the work by Henzinger, Rao, and Gabow can actually solve it. Can solve the weighted case. We don't know how to break these things.
Okay. Any other questions? Well, if not, then let me thank Thatchaphol once more, and let me take this offline. But to remind you, there is Chris Pikert will be speaking at TCS Plus 2 weeks from now. So thank you again for joining us. We are